What is the difference between a carboxylic acid and an alcohol? Let's take the examples of ethanol and ethanoic acid. Both contain 2 carbons. If you look at the differences between their functional groups, one has a carbon-oxygen double bond in the case of ethanoic acid, and the little OH tail, known as a COOH functional group. Ethanol just has C attached to an OH functional group, or hydroxyl functional group, and that is just an OH, that's an alcohol. That is what defines the two. The OH and the COOH defines whether these things have carboxyl groups or hydroxyl groups. But now, what exactly defines what an acid is? Now, an acid is defined by the quantity of H+ that is found inside of this specific acid solution. Acids are only able to act inside of a solution because that is when they are able to dissociate into H+ ions as well as other separate ions. This often occurs in bonds between really electronegative atoms and H+. Oxygen is often the sort of thing that these H+ ions will dissociate from. Because oxygen is quite an electronegative atom, it attracts the one electron that hydrogen has, and this means that oxygen will sort of keep its electron, keep hydrogen's electron, and hydrogen will then dissociate as an H+ ion, which is literally just a proton, by the way, and that will make that solution acidic. You can see this with things such as sulfuric acid, carboxylic acids, ethanoic acid, propanoic acid, etc, etc. They all have this OH bond, and this will dissociate when in a solution. Now, ethanol also has an OH bond. Things like glucose have OH bonds. They have the hydroxyl bonds. Why on earth are these not incredibly acidic? Now, while ethanol is a very toxic substance, it will create carcinogens inside of the body that I've talked about many a times before. It's not acidic, it's actually completely neutral on the sort of pH scale in a sense. And glucose is like it's a very common energy source for your body to use. While sugar isn't exactly the best thing for your body when consumed in an excess amount, it is a very necessary thing. Your bloodstream does need a baseline basal glucose blood level. Why this stuff is also completely, maybe not completely neutral, but very neutral and not acidic or alkaline enough to be considered anywhere sort of separate and special in these two categories. Why on earth do these hydroxyl groups not dissociate into another ion as well as H+ ions? And to explain this, I'm going to use the example of an ethanoate ion, CH3COO-, that sort of description that you would have seen in certain images. There are images that I'm putting up on screen. You will have the CHHH, you will then have the C, you will then have the C bonded to an oxygen, double bonded, and you will have the C bonded to an oxygen, and that O will have a little minus. That image is not entirely representative of how an ethanoate ion works, because obviously if an ethanol ion lost its hydrogen, and that would mean that the oxygen is also just left with an O minus, they are technically exactly the same things. Now, if you look at the differences between the two molecules, when I was sort of coming across this and a little bit confused, a little bit stumped, didn't really understand why, wanted to sort of obtain a little bit more knowledge in this area as to understand why these two things have different properties, I thought that the only difference between these two molecules is the carbon to oxygen double bond. So that must have an atomic effect on the other CO bond. That means that the hydrogen ion dissociates a lot more easily compared to something like ethanol. And I wasn't entirely wrong, because the COO- section of the molecule, if you imagine COO- is represented where the last O contains the minus, that's not entirely correct, because it's often if you put the COO in a brackets, so everything in there, what's outside of the brackets, will sort of have an effect on the things inside the brackets. If you put a minus outside the brackets, that essentially sort of means that every molecule there has a little bit of a negative charge. That is why carboxylic acids, and alcohols are not, because the negative charge is spread out. Because, as I mentioned before, oxygen's a very electronegative atom because of its periodicity, because of where its position is on the periodic table. It's very electronegative. It attracts electrons quite a lot. So the fact that oxygen has an extra electron here, because the sort of H+ is associated, it still has hydrogen's original electron, like in its valence shell. The oxygen that's also there up the top will be attracted to that sort of electron that is still spare in a weird sort of way. So that charge will spread out. Charges aren't sort of one and done. They're a lot more sort of probability densities. It's very confusing. But just imagine the charges sort of spread out over that sort of cloud of molecule in a way, over the right side. When that H plus ion is dissociated and it sees that that charge has now been spread out, it's not going to want to bond to that sort of ion again. It's not going to want to reassociate because that's a less attractive thing to sort of bond to. In the instance of ethanol, when it's in a solution, it probably doesn't even dissociate in the first place because it's bonded quite tightly. But in the case of carboxylic acids, a lot of the ions will dissociate. A lot of the ions will still stick together for reasons that I'm going to go through in a little bit as well. But what's interesting is that it's still a lot of a less interesting prospect because the charge is spread out for the H plus ion to sort of reattach, because it's not like, it's not, you can kind of logically imagine, it's hard to explain, but you can sort of logically imagine why that H plus wouldn't want to bond with that negative charge, wouldn't want to sort of covalently, ionically, whatever, bond with that like little cloud of charge, because it's not like a stable thing. Hard to explain logically, hard to explain in scientific terms, but logically I think you'll be able to understand why that would just seem like a less attractive prospect for something like the H plus ion to bond to. In the case of ethanol, that doesn't happen. No charge is spread out. When it gets into a solution, originally it may dissociate for literal milliseconds, like nanoseconds of time, and then it will immediately reattach because it is quite literally O minus. There's none of the CH bonds are going to be spreading out any charge whatsoever, so it is just going to literally reattach. Any ethanol that's in a solution is going to be straight up ethanol, not like an ethanoate ion and an H plus ion, etc., like you see with carboxylic acids. Now, you'd be surprised to know that carboxylic acids are still weak acids because there aren't as much H plus ions in a solution as something like a strong acid such as sulfuric acid. I'm going to compare the sort of strengths of these two acids for the rest of this video, because if you imagine the spread of charge, it's only over the right side of the molecule, and this means that while it's less attractive, there will definitely be some kind of ionization in this specific solution. The trouble is that it will still reattach that oxygen in the majority of the cases, so it's a weak acid. There aren't too many H plus ions present, and yeah, it's a weak acid. Not as strong as something like sulfuric acid, where pretty much all of its ions deassociate. If you look at a molecule of sulfuric acid, you see the S, the OO, you double bond to the O, another double bond to the O in the bottom, and then you have the two OHs either side. When these ions will dissociate, the charge is going to be spread out over the entire molecule. Oxygen, this is going to attract that sort of cloud of electron density towards it, because there's 4 oxygens on a sort of sulfate ion, so it's all going to be attracting towards each other, and the cloud basically consumes the entire molecule. Sulfur itself will play a part, because I think it's literally, if you look at a periodic table, it's one step below oxygen, which means it's still going to be pretty electronegative. I'm not going to explain the whole periodicity of how electronegativity works because it's very complicated, but it's still going to play a part as well. That's why the majority of sulfuric acid sort of molecules will dissociate in a solution. As I said, acids need to be in a solution to show their properties, because it is the H plus ion that can protonate other things that makes it acidic. If you think acids like corrode your skin and stuff, it'll be those H plus ions doing things that it probably shouldn't. I'm 90% sure anyway that's going to cause that sort of specific damage to your skin and loads and loads of other stuff. But yeah, that's pretty much it. That's all I have to say about the difference between carboxylic acids or acids and why alcohols are not acids. And I hope you enjoyed. I recommend subscribing because I love this community of young tribal people who are willing to improve themselves so much more than they already have. And good luck.